Representation is nothing but, typically if you take a group G whose order is, which I am calling it as H, okay, you could write a matrix which is a H cross H matrix, matrix representation whose dimension is also the order of the group. Okay. So, for every group element you write a matrix representation. Okay. So, how is this matrix elements going to be defined is what I am trying to say. The way to see it is that now you can treat, whenever you have a matrix which is this dimension, it should always operate on a column which is louder, H cross 1, right. So, it will be, so you could put the elements here also as if it is, each entry here corresponds to one of the elements of the group and so on. Okay. And gamma G, when it operates on the H elements, the order of the group is H, there will be H elements in this discrete group, it is going to shuffle or give you something, okay. It is going to give you some permuted combination, right, depending on how this matrix is operating. So, that is the idea. So, this will also be H cross 1 and you will see that the matrix whose dimensions is exactly the order of the group, that acts on a vector space which is also going to be H dimensional vector space. Okay. So, these matrices with this additional property. So, how do I find the matrix elements? So, matrix elements, if I want to find what is gamma ij element, because this will be a H cross H matrix. I want to find the ijth element for a particular element G. Okay. So, you are given these representations, the matrix elements are written by, this is the way we are going to write. What is the meaning of this delta? Sorry, I have given it as Gi inverse G, it does not matter, but you follow one notation. Okay. So, Gi inverse G Gj. So, this whole thing, if it becomes an identity element, if this product Gi inverse G Gj, if this is identity, then delta of E is 1. Okay. If it is else, otherwise not equal to identity, if this product can give you any element in the group G, if it is not equal to identity, then you substitute delta of that element equal to 0. Okay. So, that is the definition by which you can determine the elements of the H cross H matrix representation for the group. Okay. So, you could do this for the C4. Okay. So, if you try to write the multiplication table, let us do it for C3. Okay. C3 multiplication table is, so you can write the multiplication table to help you with playing around. So, this will be for the identity element, let us write out what will happen. So, let us first write the multiplication table. Is that right? This is the multiplication table. So, let us do gamma 1 1 of E. So, I am going to call this as 1, 2 and 3, 1, 2 and 3 in the multiplication. So, I want to find the 1 1 element of a 3 cross 3 matrix for the identity element E. So, this is going to be just E inverse E E, is that right? So, that is going to be 1. If you do gamma 1 2 of E, then it is delta of E inverse E C3. What is that? That is delta of C3, which is 0 by this definition, anything which is non-zero. So, if you put in all these things, you will find all the matrix elements associated with the identity element, and you can write the 3 cross 3 matrix for E. Okay. So, the first element was 1, second element is 0, do the other things, and you can even do not need to write everything, you can check by using this that this will also be 0 and so on. Okay. So, it will be a 3 cross 3 matrix because it is the order of the group is 3. Clear? The next question is that whether it will be reducible or irreducible. Answer? It is an abelian group. Abelian group has irreps which are one dimensional. If you have a 3-dimensional representation, the character table allows only one dimensional representation. So, it is going to be reducible. Once it is reducible, what do you have to? So, I have written it only for the identity element. Please do this for gamma of C3, gamma of C3 inverse. Okay. All of them will be a 3 cross 3 matrix. Please write it out. Okay. I have done 3 elements in the identity element, but you can work it out and see. What you have done here will give you a reducible representation. All of them are regular representations, that is the definition of the regular representations. So, and regular representation order of the group defines the dimensions of those matrices, and what you can try and figure it out is that how many reps with what multiplicity is contained in the regular representation, right. So, what is the meaning of that? Gamma regular should be a direct sum of A alpha times gamma alpha, and you need to determine what is A alpha. I will leave it to you. A similar question can be done for C4, and this is the way to figure out the representations for the group, but the dimensionality of the representation is like the order H cross H matrices. Those are regular representation which are reducible, and you find number of times each of the irreps appear in this. Okay. So, this I am not going to do, we have done this elaborately for the one of the groups of C3V, one of the representation, but this representation I will leave it you to check and do the C4 also. Okay. Yeah. Yeah, so this is a matrix. Matrix will multiply with a column vector. Huh? So, for every matrix representation, linear algebra tells you that it can act on a vector space which is H dimension. That is all I am trying to say. So, this will give you a new column vector. So, technically you could have written it as x1 up to xh, it will go to x1 prime, x2 prime and xh prime. But this elements which I am writing here, you could also rewrite it as if it is G1, G2, Gh. These will be some permutations which will happen. It will become, let us say G1 becomes G2. So, you could have some permutation, depends on the element, identity element does nothing, and then other elements can do some kind of a, that is exactly what is happening in your multiplication table. If you operate on C3, it is taking you, the identity element becomes C3, then C3 becomes C3 and so on. So, this any row or any column is the permutation order of the elements of the group. That is what the regular representation captures, and formally we could say that the regular representation elements can be obtained by using this procedure. It is equivalent, yeah.
Regular representations are h and the permutations are h factorial. So, it would be subset of those h factorial.
It will be, Cayley's theorem tells you that I am looking at a specific group, not all the permutations I am going to look at it. It is pertinent to a multiplication table, right, yeah. Okay. So, this tells you that you can write the characters. I have not written the characters, I just wrote the matrix representation. You have to take the trace of it, because you can determine what is A alpha from the characters, right, and obtain A alpha. Okay. Okay, so this also I have gone through for you the basis column. Just like I said, whenever you have a matrix representation, it will act on the corresponding vector space. If the irreducible representation is one dimensional, then the basis will be one dimensional. What is the right basis in your position coordinate system? In the context of point groups, you are going to take principal axis to be along z axis. So, the z coordinate is a good basis for the irreducible representation A1, right. We did this many times. Unit representations of most of the point group will have z as the basis, we saw. The next one is A2, is another irrep. The Mulliken notation tells you that A is used whenever the principal axis character is +1 in the one dimensional representations. So, A we use the symbol A, and now what you have to do is every element of A2, when it operates on the axial vector. So, if you operate identity element on the axial vector, this will be axial vector, right. If you operate C2 on the axial vector, what happens? X will change sign, y will change sign. So, axial vector will not change sign, right, +1 times this axial vector. And if you do sigma xz on the axial vector, what happens? Y will change sign. So, it will go to minus of Rz. The axial vector z component is something like x cross x. So, you can write this Rz as if it is like your angular momentum component. So, you could write it as x py minus y px, for example. The Lz component is an axial vector. So, whenever I do the sigma xz on x, nothing will happen. Sigma xz on py, what happens? Y component changes sign. So, there will be a negative sign. Similarly, here y coordinate will change sign, but Px, which is the momentum x component, will not change sign. So, essentially you will get a negative sign on the other side, and that is exactly what you have here. -1 is the number which you have to get whenever you operate sigma x z element on the A2 irrep. Similarly, if I operate sigma y z, again it will be minus by the same argument, but instead of your y it will be the x component which will change. Which one? This is r cross p, no, the z component of the L vector it is exactly this. Okay. So, that is an axial vector. I explained what is an axial vector in the last lecture. When you do an inversion, the momentum vector as well as the position vector will change sign, but axial vector components will not change sign. That is why it is called as an axial vector. R is a polar vector, P is a polar vector, but R cross P is an axial vector. If you write it in components, you can see that whenever you do this operation E C2 sigma x z and sigma y z on the axial z component, you find it to be -1 times R z. Okay. This eigenvalue which you find is what is important. So, you have +1, +1, -1 and -1 in the one dimensional representation, and that are nothing but the characters of the A2 representation. So, the basis which respects the A2 representation is not the z component, but the axial component, axial vector z component. Is this clear? It cannot be z. Why it cannot be z? If it was z, you will get only the A1 irrep. Mirror reflection on the xz plane will not change, it will give you a +1, right. If you just did it on z coordinate or not at axial z coordinate, and this will also be +1. So, the +1, +1, +1, +1 will happen for z coordinate, +1, +1, -1, -1 will happen for the axial vector z component, which is denoted by R subscript z. Is that okay? Yeah. Yeah. So, whenever I am going to write some irreducible representation, I have at my back of my mind a matrix representation. Typically, matrix should operate on a vector space which should have a basis. If it is if the irrep is 1 cross 1 matrix, the basis should be one dimensional, and the first easiest one which you would like to look at it is the basis in the position space. Okay. You can look at it at abstract vectors also, because when you call it as a vector, what is the definition of a vector? If it transforms exactly like the components of a position vector, you call it as a vector, right, polar vector to be very specific, and then you can give meaning to various other vectors once you have this basis. So, that is the advantage. The irrep, matrix representations of these irreps will act. Good point, yeah. So, all of them in this case C2V is all one dimensional, it is an abelian group, it is one dimensional, but we can also look at the C3V where we have two dimensional representation, right. So, this is the procedure. You take the group element, operate on a basis, find what number you get at least for the one dimensional irreps, and match for the z, it turns out to be the A1 irrep. So, that is why the basis becomes z, and for Rz, as I have displayed on the board for you, it corresponds to the A2 irrep eigenvalues, Okay. It is an eigenvalue equation only for one dimensional irreps, because the vector space is one dimension. Okay. So, similarly acting on axial vectors, I have not done the other things, x coordinate, y coordinate, ry and rx, please check it out, that you will see that the corresponding eigenvalue, the set of 4 eigenvalues which you get when you operate these group elements like the way I did it, do it for x, do it for ry. So, these two are two independent bases. You can either work with a basis which is the x component, or it can be ry which is a axial y component. Okay. These two are, there are two different bases which you can use for the same irrep. That is all I am trying. Do not confuse that to be a 2-dimensional basis. It is two independent one-dimensional bases. Either you can use the x component as a basis, or you can use the y component axial vector as a basis. Is this clear? Okay. So, that is a way to fix the closest basis which is in your position space. The reason why we are doing all these things is that all the operators or observables in nature can be either treated to be a vector or tensors, right. You know that you have electric dipole moment. Electric dipole moment is what? Is a vector, right. Then you also have something called as a quadrupole moment tensor, right. These are things which are objects which are observables in nature. Whenever I am going to look at observables, suppose I look at the electric dipole moment and I am going to look at only the z component of the electric dipole moment, which is the right irrep for that operator. If I ask, I look at this table, look at this basis vector for position coordinate z is the A1 irrep. So, I will say that the z component of the dipole moment operator right, this is the notation for the dipole moment operator. This should be belonging to the A1 irrep, that is the way I will write. This is another reason why I need to know the basis, because we are going to do electric dipole moment transition interaction, which can lead you to a transition from one energy level to another energy level, and then we need to play around, are these observables belonging to which irreps. Then you have to resort to looking at the character table and the basis states, and it will help us to see which irreps it belongs. If I ask for the x component of the dipole moment vector, then the corresponding irreducible representation to which it will belong will be the B1. Okay. Is that clear? So, that is where this basis state will play a crucial role in getting. So, and also the basis states will change when you go from one group to another group, that also you should remember. If I start with a system with certain symmetry, you first draw the character table. After you draw the character table, you write the character table, you write the basis, then the operators will belong to one of those irreps. That is the next step. Okay. So, we will come to this systematically, but as of now I assume you understand now how one frames the primary basis. Why primary? It is not involving any quadratic powers of these coordinates, and the primary basis column which I have written is these possibilities for the A1, A2, B1, B2. Is this clear to you? Okay.